The next part of this lecture concerns solubility. We're going to look at solubility in water. From earlier chapters, you know that water is a polar molecule because oxygen is more electronegative than hydrogen, resulting in bond dipoles and an overall molecule dipole. Water is represented with this space-filling model here, where the yellow represents the oxygen and the two pink are the hydrogen. Water is somewhat different than organic compounds, which are based upon carbon. This is an example of methanol. Carbon-hydrogen bonds are considered nonpolar. Remember that they have an electronegativity difference of 0.4. On the other hand, the carbon-oxygen-hydrogen area of the molecule would be a polar region. This is represented by the space-filling model shown here, where carbon is the green sphere, oxygen is still yellow, and the pink are the hydrogen. So let's consider liquid water versus liquid methanol. The intermolecular forces that attract these molecules to one another are dispersion, dipolar, and hydrogen bonding. If we think about dissolving methanol in water, here are the stages of the dissolution. Notice that I have blue dashed lines to indicate hydrogen bonding and some red dashed lines to indicate dispersion interactions. First, in order to dissolve methanol in water, we need to break the intermolecular forces of the solute. So let's move the methanol molecules further apart. This requires energy. This is known as the enthalpy change of solute, and it is positive in value. Next, we need to make room in the solvent for the methanol. So we need to break the intermolecular forces of the solvent. This will also be positive, and this is represented as the enthalpy change of solvent. So now we have moved the water molecules a little further apart so that the methanol can fit in there. Our last step is to make intermolecular forces between the solute and the solvent. So let me put the methanol in the water and now think about what types of intermolecular forces occur. Mostly it's hydrogen bonding between the OH of the methanol and the OH of the water. We say that when the solute, which is methanol, is surrounded by the solvent, it is solvated. If that solvent happens to be water, we say the solute will be hydrated. This enthalpy change is known as delta H mixture. We are forming intermolecular interactions, or bonds, if you will, so delta H mixture has a negative sign. If we think about the solution process of methanol in water, no gases are created or consumed, so the sign of delta S is close to 0. In order for this to occur, first we have to break the intermolecular forces of the solvent, and then break the intermolecular forces of the solute. Both of these have positive signs, so they are endothermic and not preferred by Mother Nature. The last part of the process is to make intermolecular forces between the solute and the solvent. This is delta H mixture, and it is negative or exothermic. If we look at the entire enthalpy change for delta H of solution, it is the sum of these three enthalpies that I've just described. Since delta S is close to 0, the free energy change that occurs is going to be mostly governed by the value of delta H. For the solute to dissolve spontaneously, delta G needs to be negative. So what needs to be true? Well, if we look at the sum of these three processes, delta H solute and delta H solvent are positive, so it needs to require not very much energy to break the intermolecular forces from solute to solute or solvent to solvent. Delta H mixture is negative, So we need good intermolecular forces between the solute and the solvent. We need the negative value to be greater in magnitude than the positive values. Because if delta H solution is negative, delta G is most likely negative as well. Because we need good interactions between the solute and the solvent, this criteria is described as like dissolves like. If the solute and solvent have good interactions, generally the material will dissolve. Let's look at a different molecule now dissolving in water. Instead of methanol, let's try octanol. Octanol is 8 carbons long with the carbon, oxygen, hydrogen. So you notice we have a nonpolar region in red and a polar region in blue. The space-filling model of octanol kind of looks like a caterpillar to me. There is hydrogen bonding in one region of the molecule, but the rest of the intermolecular forces are just dispersion forces. Although octanol is a much larger molecule than methanol. Let's think about the dissolution process. First, we need to separate the solute molecules. This is going to require a larger amount of energy because octanol is much larger in size than methanol. Then we need to make a much larger space in the solvent, again because octanol is much larger. When we look at delta H mixture, which is our exothermic process, we will get some hydrogen bonding between the OH of the water and the OH of the octanol. But the tail of the octanol, the carbon and hydrogen area, is not going to want to form intermolecular interactions with the water. So delta H solvent of this process is typically positive. This means that delta H solute and delta H solvent are positive and large, and delta H mixture, although negative, is very small. Delta G tends to follow delta H in this dissolution process. So if delta H solution is positive, delta G is typically positive. So this means a non-spontaneous process, meaning octanol will not dissolve in water. It will actually float on top as a less dense material. So we say the octanol is insoluble. This brings up some vocabulary words, hydrophobic and hydrophilic. Hydrophilic means water-loving. This is a term used to describe a compound with polar regions or even a charge that forms strong bonds with water, meaning strong intermolecular attractions. An example might be SO2. This is a polar molecule. It's capable of hydrogen bonding. So we would say that SO2 is hydrophilic. Hydrophobic, phobia, of course, means fear of, or maybe water hating. This is a term used to describe a compound with nonpolar regions that forms weak intermolecular forces with water and will not dissolve. How about octane? Octane is a major component of gasoline, and I'm sure you know that when one of these tankers springs a leak, the octane tends to float on top of the water and not mix in. Octane, we would say, is hydrophobic. This would be because delta chi for a carbon-hydrogen bond is 0.4, such that carbon-hydrogen bonds are considered nonpolar. But what if you have polar and nonpolar regions in the same molecule? A great example is acetone. Acetone has a polar region by this carbon-oxygen double bond, so we would call that the polar handle, and this is capable of hydrogen bonding with water. Acetone also has nonpolar regions or nonpolar handles, which would not interact with water, but would interact with an organic solvent. Here again, size of the region matters. If we look at sort of the acreage of the hydrophilic and the hydrophobic, there's less hydrophilic acreage, but remember that hydrophilic interactions tend to be stronger than dispersion forces. So although this is a smaller region, acetone is very well balanced for both types of environments. Acetone dissolves many organic substances, but it's also miscible with water. That means it mixes very well with water. So acetone can be in either the nonpolar or the polar world. But if we make the hydrophobic region larger, such that the polar handle acreage is much smaller than the nonpolar region, we wind up with a material that is only slightly soluble in water, but very soluble in organic substances. In fact, here's a series of alcohols, and we're going to look at the solubility in hexane, which is nonpolar, and water, which is polar. All of these are alcohols, so they all have that oxygen-hydrogen area, so that would be their polar region. And then they all have these carbon tails on them, which would be their nonpolar region. So let's look at the different types of solubilities we might have. We'll start with methanol. Methanol is infinitely soluble in water. You can add as much to water as you would like. But the solubility of methanol in hexane is low. It's only 0.12 molar. So methanol is more polar than nonpolar. Remember that although the acreage looks the same, hydrogen bonding is stronger than dispersion forces. Now let's look at ethanol. We're increasing the nonpolar amount. Ethanol is infinitely soluble in water, but also infinitely soluble in hexane. Ethanol can live in both worlds. So can propanol, equally soluble in polar or nonpolar solvents. Once we get to 4 carbons, things change. Any one of these materials is infinitely soluble in hexane, but the solubility in water decreases. This is butanol, and its solubility is 0.11 molar. If we move to pentanol, now we're down to 0.03 molar, and if we move to hexanol, we're now down to 0.006 molar. So I trust you can see that once we get to about 4 times the nonpolar region as the polar, we wind up being more nonpolar than polar. Here are some other examples. Which solute is more soluble in water? HBr or Br2? Water is, of course, polar, and like dissolves like. So we want to find polar to dissolve in polar. So HBr is polar, Br2 is nonpolar. HBr would be more soluble in water. Which solvent would best dissolve iodine? Iodine is nonpolar. Water is, of course, polar. Carbon disulfide, shown here, is like carbon dioxide, except with sulfur, and it turns out to be a nonpolar solvent. So nonpolar goes with nonpolar. Which solvent would best dissolve potassium chloride? Potassium chloride is ionic, so we might want to call that superpolar. Water is polar, carbon tetrachloride is nonpolar, so potassium chloride will dissolve better in water. Now let's try some organic type compounds. We'd like to know, are they more soluble in water, which is polar, or carbon tetrachloride, which is nonpolar? Let's look at this first compound. Nothing but carbons and hydrogens. That is a nonpolar material, so it would be more soluble in carbon tetrachloride. Let's look at B. Seems to have a lot of nonpolar and also some polar. But you can see that the nonpolar area is much greater acreage than the polar. So carbon tetrachloride would be a good guess. How about C? Polar. So it belongs in water. And D has a nonpolar tail, but a superpolar region. It's ionic. So this belongs in water. Now it's time for your student questions. Decide if each of the following substances would be more soluble in water, which is our polar example, or hexane, which is our nonpolar example. So first decide for lithium acetate, which would it be more soluble in? And then for propane, which would this be more soluble in? Here is another example. Decide for the first compound, which is dipropyl ether, and the second compound, which is methanol. For this last one, we have a nonpolar tail and some ionic character, and then this compound.